name is Lucas, and welcome to this talk on using artificial intelligence for 3D vision. So the scope is that we start with an introduction on the broad field of computer vision, 3D vision in particular, and a very interesting problem known as structure from motion. Then I will present a selected work from my PhD studies, where I used AI to learn structure from motion. And this will be broken down into a small crash course on artificial intelligence, followed on the topic of considering geometric elements as words, an overview of the artificial intelligence model architecture, and finally the results and the conclusions from the work. So, computer vision in its entirety, it's essentially the field of automatically processing and analyzing what you see in an image so that the computer can do it for you. And the applications are pretty vast. Famous examples are image classification. For instance, this example on the bottom left. This is like a 2D vision example. Using visual captures to determine whether or not a human is entering a web page. I'm sure you're all quite familiar with that one. And then we have, for instance, this app, IKEA Place, which uses 3D vision and augmented reality. And in that app, you can essentially place a piece of furniture wherever you want in your own room artificially, and you can see it on your screen. And this uses some pretty advanced 3D vision behind the scenes. And 3D vision is also my main focus of interest. And to give a brief intro on this topic, let's start with the most core concept, I would say, which is camera projection. So in photography, what we are doing is essentially that we flatten the 3D world onto a 2D image. And after we do so, each pixel in the image, it will contain information on what color and intensity the incoming light ray had that hit that part of the camera lens. So essentially, we know the color, we know the intensity, and very importantly, depending on which pixel we are talking about, that tells us from what direction the light came in. So each pixel corresponds to a certain direction in 3D space. That is the point. And after you have projected a 3D point via a light ray, we are often interested in, based on an image, actually determine things about the 3D reality and go backwards in this projection process. And this is not immediately possible. So the thing that we have lost here is the depth. So when you project and flatten, there's no way to directly know at what depth that 3D point was located that got projected into the camera. In the illustration here, you can see 3 cameras. Each of them has a image visualized in front of it. And in each of them, 2 3D points are projected. And they're color-coded so that you can match them here. Same image. Now, in order to explain what the problem that is of primary interest for me, called structure from motion, what that is all about, let's focus a little bit more on this picture here. So what do we see in this picture? To start with, we have these projected points, 2D points in each respective image. We call these the projections, and this is considered information that we have from the start when we are facing the structure from motion problem. So the structure from motion problem is essentially to calculate everything else about the 3D reality, given that you have this specific information, that you know where certain points are located in these images at what pixels. And given this information, what we want to find out is it's the views, or also known as cameras. So we essentially want to determine each of these 3 cameras, where are they located in 3D space, and in what exact direction are they facing, position and orientation. And finally, we have these 3-dimensional points that we don't know from the start, because we only have access to the flattened projected 2D points in each image. But this we want to determine as well. So we want to find the 3D scene points, and we want to find the camera positions and orientations. And if we manage to do this, we have solved the problem of structure from motion. There's a lot to say about the problem. There are a couple of different flavors on how to approach it. But usually you can roughly divide it like this in 3 subparts from left to right here. And on the left hand side we have the feature detection and matching. This is not something we will consider. That's essentially the task of determining, like, given a lot of images and points in the images that you have detected, match them with each other and actually determine that what you see at pixel A in the first image is the same as pixel C in another image. Do this matching. After that, we perform a reconstruction. We essentially solve the structure from motion problem, and we calculate exactly what I said, the camera positions and orientations, and the 3D scene points. This may not be easy to do at very high accuracy, but it's important that it's done robustly, so that, let's say that some of these point matches from the first step were not 100% correct. It's crucial that we don't trust them 100%, and we handle it in a sensible way, even if some of them are bad. So that's the main focus in this middle step. And finally, on the right hand side, we have what's known as bundle adjustment. And that's essentially like a refinement step, where the solution is a bit improved in order to you do small adjustments to the 3D points and the camera positions that lead to the projected points to end up more closely to where you actually observe them in the images. And the middle step here is the only step that we will focus on in this work. So, given the huge success of artificial intelligence, we may actually ask the question, what about this problem of all the problems in the world? Can AI handle this one as well, perhaps? Can AI solve structure from motion? And let's say that it's possible. What would the benefits be? So the benefits that I can see, they are like, for one, it may result in quite significant speed-ups. Because the conventional iterative approaches, they can be quite time-consuming. And the other thing is that there is a potential to learn which false point matches to ignore. Again, the conventional approaches to handling the false point matches, they are quite rudimentary. They are essentially based on trial and error, but there are many variations of this, but they're known as RUNSEC. Just to mention a little bit about what artificial intelligence is. When we say AI, we very often actually mean machine learning, which is a more specific method used for AI systems, where we train a machine to do a task based on presenting it with data. That's the typical scenario. It's essentially a certain method to teach a computer to perform a task by showing it many examples, or also known as observations. Then it's built. You build an optimization problem that punish bad performance, and you can actually use conventional techniques to find a model that performs as good as possible on solving your task. And then the end goal of this is not that it performs well on the data that you presented, called the training data, but the end goal is that it will generalize well. And there are many different techniques on focusing on this crucial part that is a little bit elusive as well. But that's the main thing we want to get out of it. We want it to perform well on new data that was not seen before. And of particular interest in these days are the large language models, such as ChatGPT and the rest. They are all built on what's known as the transformer AI model. This was presented in 2017, and it's built on a core concept known as attention, where the AI model learns on which words to pay particular attention. These transformers, they have been applied a lot on sentences of words, but they are applicable on any sequence, or also on unordered collections of anything really. In the nomenclature, we refer to these things that we have a sequence or collection of as tokens, but for the language case, these typically corresponds to words or subwords. But it can also be very abstract entities. It can be parts of images, and it's very flexible in this way, the transformer architecture. So it can be used for many things and has been applied for many things. And this is the one that we want to try to apply for structure from motion. Coming back to our famous little picture, what if we take these geometric elements that we see in the picture and we regard them as our words or tokens that these transformer models should operate on? So instead of a sequence or collection of words, we actually have a collection of these geometrical things that we see in the image. And these are the things you want to process and predict. So first we have the projections, and this will be the input to the model, since this is the thing that we know from the start. So we have a bunch of 2D points. And each 2D point will be regarded as one word, essentially. And what we want to produce, that is the 3 cameras in this example, and the 3 scene points, the 3D points. And all of these will be considered as words. And in order to do so, we define a couple of feature types corresponding to these different geometric entities. And we organize them in such a way that we put them in a matrix where each row corresponds to one camera view and each column corresponds to one scene point. And each geometric entity may then carry information in a so-called feature vector. That is a standard representation of information in machine learning models. It's a bunch of numbers, essentially. So for our 3 cameras, we have these 3 view feature vectors. We have for each of the scene points. In the illustration, it was 3 scene points, but in this example, it's 6 of them. And here you have projection features. So this is essentially, it's a sparse pattern. It's not defined everywhere, and it depends on which scene point is visible in which camera. So for example, the green arrow here points at the projection or image point, 2D point, corresponding to the fourth scene point when projected into the second camera. Which pixel will it end up at? And that is the projection feature here. Finally, we have also a global entity that doesn't concern any of the geometric elements specifically. But what you see now, this is all of the words that we will throw our lovely transformer model on. And the input to this model is going to be projection features. This is actually the entire architecture. I don't think I can go into detail to explain this, but what goes into the model is the projection features. That is the matched image coordinates, 2D points. And what we get out in the end is the predicted camera positions and orientations and the 3D scene point positions. This model is trained on 12 scenes with known 3D point clouds and camera positions. And the results here, so our results are in the two columns on the left. So you have first, before refinement, you have a crude result in the leftmost column called inference. And then it says plus BA for bundle adjustment in the second column. And that's the result that you get if you do the refinement as well. And that's the one that gets interesting, actually. And this can be compared to the deep permutation equivariant structure from motion model. It's a competing previous model. And we can see that quite consistently outperform them. That was also a learned model. That's why it's interesting to compare to, and it's quite related. Ours builds upon it. And in the rightmost column, that's not a learned model. That's a conventional structure from motion solver, which is consequently more time-consuming. But as you can see, this is more or less regarded as a ground truth, and we get results that are relatively close to it. And considering the execution time, we see that we perform about 5 to 10 times faster execution time compared to that Colmap method, which is established non-learning method. We get quite similar results. And that's it for me. Thank you very much for the attention.